Why does everything in the universe spin? Here is something that should genuinely bother you. Every single thing in existence is rotating. Every atom, every star, every world, every galaxy, all of them turning, all of them holding angular momentum that, according to physics, cannot simply vanish. And yet, when scientists measure the universe on the largest possible scale, the total rotation appears to equal zero. Every individual part is spinning, while the entirety of the cosmos remains completely motionless. That is either one of the strangest coincidences ever to exist in nature, or it points to a deeper rule of reality that nobody has successfully explained. And if that perfect balance were ever disturbed, even by the tiniest amount, Kurt Gödel demonstrated that time travel could suddenly become physically possible, carrying consequences far beyond what most people have ever considered. We are about to trace rotation from the smallest scales known in physics, all the way up to the structure of the universe itself, and along the way we will discover that the cosmos keeps flawless accounting records for something whose true origin remains completely mysterious. We will also examine why time travel may not be pure fantasy at all, thanks to one mathematician's remarkable solution to one of Einstein's equations. So get comfortable, and let's slowly step into this together. Part 1. The rotation hidden in plain sight. Nothing around you is truly motionless. Not the seat beneath your body, not the ground supporting it, not the air drifting softly across the room, not the drink slowly losing heat beside you, not the device resting in your palm, not the walls surrounding you that seem so solid and unmoving. Every object in your immediate world, every surface you have ever touched, every structure you have ever stood upon or leaned against, is in motion, and not in a slow or subtle way that barely matters. The movement is enormous, relentless, and far beyond anything your senses are capable of noticing. If you could somehow step far outside this system and observe it from a distant point in space, what you would witness would not resemble stillness at all. You would see a vast, coordinated rotation happening at extraordinary speed, so balanced and so smooth that from the inside it disguises itself as complete stability. At this exact moment, if you are anywhere close to Earth's equator, your body is traveling eastward at approximately 1,674 kilometers per hour. That speed exceeds the cruising velocity of many military aircraft. It is even faster than the speed of sound through air at sea level, which is roughly 1,235 kilometers per hour. You are continuously moving faster than sound itself, carried across space on a rotating sphere that completes a full turn every 23 hours, 56 minutes, and 4 seconds. Yet none of this feels real to you. There is no roaring wind pressing against your skin, no trembling beneath your feet, no sensation at all that you are racing through space at incredible speed. The room feels calm, silent, still. Everything around you seems fixed in place, quietly maintaining the illusion that motion does not exist. The reason your body notices none of this comes from one of the most elegant principles ever discovered in physics. It is known as an inertial frame. When an entire system moves at a constant speed, or when changes in that motion are so gradual that your nervous system cannot register the acceleration, your brain loses any reliable way to tell the difference between being perfectly stationary and moving across a giant conveyor belt at 1,500 kilometers per hour. Human senses were never designed to detect steady motion itself. They evolved to notice changes in motion. Sudden acceleration, sharp deceleration, abrupt turns. Those are the things you feel instantly. But smooth, uninterrupted rotation occurring at a fixed rate is interpreted by the brain as stillness. This is not a flaw in perception. It is actually an accurate description of the environment from inside your own reference frame. Within the rotating system, the laws of physics behave exactly as though everything were at rest. Only by comparing your frame of reference to something external does the hidden motion become obvious. And this is where things become truly strange. The atmosphere surrounding you is participating in that same rotation. The oceans are as well. The immense jet streams flowing through the upper troposphere at heights between 10 and 12 kilometers are rotating too. Every layer of the Earth system moves together, locked into synchronized motion by gravity and friction, forming a gigantic spinning structure made of air, water, rock, and metal. The atmosphere does not remain behind while the planet turns beneath it. It stays attached. It rotates together with Earth, held by gravity strongly enough to keep trillions of tons of gas and liquid moving almost perfectly in step with a spinning sphere of iron and stone. There is, however, one region where this synchronized co-rotation weakens just enough for the planet's rotation to reveal itself directly as a measurable physical phenomenon. That phenomenon is called the Coriolis effect. When large masses of air attempt to travel in straight paths across the surface of a rotating world, the rotation of that world bends their trajectories. In the northern hemisphere, moving systems curve toward the right. In the southern hemisphere, they curve toward the left. Hurricanes and cyclones rotate counterclockwise in the north and clockwise in the south, not because fluids naturally prefer those directions, but because the planet beneath them is spinning. The Coriolis effect is nature's way of exposing Earth's hidden rotation on a planetary scale. Every satellite image of a hurricane is evidence that you already exist inside a rotating reference frame. The spiraling structure of those storms is not random. It is Earth signing its own motion into the clouds. But even that only scratches the surface, because rotation does not end with planets, oceans, or atmospheres. It continues all the way downward into the deepest layers of physical reality. Hidden within matter itself, at the most fundamental level modern physics currently understands, exists a phenomenon known as quantum spin. Every fundamental particle possesses this property. Mathematically and experimentally, it behaves like a form of angular momentum, despite the fact that it cannot literally be described as a tiny object spinning through space in the ordinary sense. And there is a remarkable, almost haunting signature of this microscopic spin that can be detected with the proper instruments anywhere across the cosmos. It is known as the hydrogen hyperfine transition. Hydrogen is the most common structure anywhere in the known cosmos. Around 75% of all ordinary matter throughout the universe is made of hydrogen. Inside a single hydrogen atom, one electron moves around one proton, and both of those particles possess their own intrinsic quantum spin. In most cases, the spin of the electron points in the opposite direction of the proton's spin, because that arrangement represents the lower energy state. But from time to time, the electron flips so that its spin lines up with the proton, creating a slightly higher energy configuration before eventually flipping back again. When it returns to the lower state, a photon is emitted. That photon always carries an extremely precise frequency: 1,420,405,751 Hz. Exactly 1.42 gigahertz. Not close to it. Not an estimate. Exact. The signal is so dependable, so stable, and so universal that radio astronomers rely on it as a standard marker for mapping hydrogen clouds throughout the galaxy. The universe continuously broadcasts this frequency from every hydrogen atom that has ever experienced this transition, meaning the signal is arriving from nearly every observable region of space. Every hydrogen atom inside your body, inside water, proteins, DNA, and the fluid surrounding your cells is involved in a quantum rotational interaction. The spin of the proton and electron is not some event happening to hydrogen from the outside. It is part of hydrogen's identity itself. Rotation is built directly into the structure. It is intrinsic. It does not need to be activated, started, or sustained. It simply exists as one of the most basic properties of matter. So let us pause and recognize where this leaves us. Your body is spinning at more than 1,000 miles per hour while standing on the surface of Earth. Earth is orbiting the Sun at 30 kilometers per second. The Sun travels through the Milky Way at approximately 230 kilometers per second. The Milky Way itself is moving toward the Virgo cluster at close to 600 kilometers per second. And underneath all of that, within the atoms that form everything you are capable of seeing or touching, exists a level of intrinsic quantum spin that never slows, never fades, and never needs energy input to continue. Motion is not merely something that occasionally occurs in the universe. Rotation is the default condition. It is the natural ground state of matter embedded inside gravitational systems. Objects that appear still, bodies that seem motionless, surfaces that look at rest, these are only local illusions created by your frame of reference. The universe, from the quantum world all the way to galactic structures, does not really do stillness. It spins. And if that is true, if rotation is truly this universal, this persistent, and this fundamental, then the question that should genuinely disturb you is not why things spin. The real question is whether anything, anywhere in existence, ever truly stops. There is a law in physics so deep and so universal that it works the same way whether you are describing the spin of an electron or the orbit of an entire galaxy cluster. That law is this: angular momentum is conserved. The sentence sounds simple enough. It is not simple at all. Fully understood, it means that any object or system that is spinning or orbiting, as long as no external torque or twisting force acts on it, will continue rotating forever, not slowly winding down, not eventually coming to rest. Forever. If every source of friction, drag, and gravitational disturbance could somehow be removed, leaving a rotating object completely isolated, it would still be spinning 1,000,000,000,000 years from now, 10 trillion years from now. Even at the heat death of the universe, if matter still existed and still possessed angular momentum, it would continue rotating. Conservation of angular momentum is not a rough guideline or a loose tendency. It is a mathematically exact law that remains valid across every physical scale humanity has ever tested. This explains why the hierarchy of spinning systems in nature appears the way it does. Begin at the smallest level. Every fundamental particle, electrons, quarks, neutrinos, photons, possesses a property known as spin. This is quantum spin, not ordinary classical rotation, and we will return to it later because it is honestly one of the strangest ideas in all of physics. But for now, what matters is that it behaves as angular momentum. It comes in quantized values. It is conserved. It belongs intrinsically to the particle itself, not something gained later or something that can simply disappear. Electrons carry a spin of 1/2 in units of the reduced Planck constant. Protons also carry a spin of 1/2. Photons possess a spin of 1. Higgs bosons have a spin of 0. These properties never change. An electron will always remain a spin 1/2 particle. It cannot suddenly become spin 0. Spin is woven directly into the identity of the particle. Move upward one level from there. Atoms inherit angular momentum both from the spins of the particles inside them and from the orbital angular momentum of electrons moving around the nucleus. Molecules then inherit angular momentum from the atoms that compose them. These angular momenta merge and influence one another according to extremely strict quantum mechanical laws, producing unique rotational patterns for every type of molecule. Those patterns are the exact reason astronomers can determine what distant interstellar gas clouds are made of from light years away, simply by studying the particular microwave frequencies those molecules absorb or release while rotating. Now move to the scale of planets. The solar system emerged from a collapsing cloud of gas and dust around 4.6 billion years ago. That enormous cloud was never perfectly smooth or motionless. Tiny irregular currents already existed within it. Local shifts in velocity produced by turbulence from nearby supernova shockwaves, gravitational effects from neighboring clouds, and the naturally chaotic behavior of fluids on astronomical scales. Once gravity began pulling the cloud inward, those small motions became enormously amplified. This is where the physics becomes important. When a rotating object shrinks, its rotation speeds up. It is the same effect seen when an ice skater spins faster after pulling their arms inward. As the cloud contracted, its spin accelerated. The faster that rotation became, the more the outward centrifugal effect pushed material away along the plane, perpendicular to the rotation axis. The outcome was not a sphere, but a flattened disk, a rotating protoplanetary disk, with the young sun forming at the center, while the remaining matter circled around it in progressively organized rings. The planets eventually formed from the material inside those rings, building themselves through repeated collisions and gradually inheriting the angular momentum already present in the disk. Earth's present-day rotation is a direct remnant of that ancient turbulence inside a cloud of gas billions of years before the planet itself came into existence. The spin existed before Earth did. Earth formed around that spin, now moved to the scale of stars. Stars are created through the same mechanism, only on a much larger scale. A molecular cloud collapses under gravity, strengthening whatever angular momentum it originally possessed. Young stars rotate extremely quickly. Some complete a rotation in only a few hours, vastly faster than the sun's current rotational period of about 25 days at the equator. Across millions and billions of years, stellar winds and magnetic interactions slowly remove angular momentum, reducing the rotational speed. But the spin never truly vanishes. It is transferred elsewhere. The sun's present rotation, although slower than during its early life, still represents conserved angular momentum inherited from interstellar gas long before the solar system was born. Now move upward again to the galactic scale. The Milky Way is a barred spiral galaxy, approximately 100,000 light-years across, and containing somewhere between 100 billion and 400 billion stars. Nearly all of those stars orbit the galactic center within roughly the same plane and in roughly the same direction, forming a coherent rotating disk. The galaxy requires somewhere between 225 million and 250 million years to complete a single rotation at the sun's distance from the center. One complete galactic orbit. During Earth's entire 4.6 billion year history, our planet has completed only around 20 journeys around the Milky Way. For most of cosmic history, galaxies have been slowly turning, redistributing matter, building structure, and behaving exactly as rotating gravitational systems tend to behave. They create order. The essential idea here is that angular momentum is not created anew at these different scales. It is passed along and redistributed. The Milky Way did not somehow invent its own rotation from nothing. It inherited that motion from the angular momentum already present in the collapsing matter that formed it, which inherited its motion from the turbulent rotational conditions of the early universe, which, and this is where things become difficult to explain, must itself have inherited that angular momentum from an even earlier source. Angular momentum functions almost like a memory system woven into the universe itself. Every rotating object you observe carries a preserved history of motion extending backward, continuously, to conditions that existed before the object itself was ever formed. Accretion disks provide perhaps the clearest and most dramatic example of this principle. Whenever matter falls toward a massive central object such as a newborn star, a neutron star, or a black hole, the material almost never moves straight inward. Nearly all incoming matter possesses at least some angular momentum, relative to the object at the center. As that material falls inward, angular momentum has to remain conserved, meaning the matter cannot simply collapse directly onto the central body. Instead, it spirals inward and forms a disk. The inner regions of the disk rotate faster, while the outer regions rotate more slowly. Matter gradually drifts inward, as angular momentum gets transferred outward through the disk by turbulent viscosity and magnetic instabilities. The final result is an accretion disk, one of the brightest, most energetic, and most structurally beautiful phenomena in astrophysics. And the entire mechanism is driven by nothing more mysterious than the conservation of angular momentum acting on falling gas. Rotation is not a phenomenon that requires a separate explanation at every scale we observe. Whenever matter possesses angular momentum inside a gravitational field, spinning naturally emerges as the expected result. The deeper mystery, and the one we will continue orbiting throughout the rest of this documentary, pun fully intended, is not why particular objects rotate, but where all the angular momentum of the universe originally came from, and why, after everything is added together, the total seems to come astonishingly close to zero. Part 3. The Galactic Clock Mystery. The dinosaurs never looked up at exactly the same sky twice, not only because stars slowly shift relative to one another across geological eras, which they absolutely do, but because the entire solar system, the sun, and every planet around it has been traveling around the center of the Milky Way throughout Earth's entire 4.6 billion year existence. At the orbital velocity, scientists currently calculate around 230 kilometers per second. The solar system completes a single revolution around the galaxy in approximately 225 to 250 million years. That span of time even has its own term, the galactic year, sometimes called the cosmic year. Earth today is roughly 20 galactic years old. Since the formation of the solar system, the sun has circled the Milky Way about 20 times. Every one of those galactic circuits lasted as long as the entire Phanerozoic eon, the full history of complex animal life, all 5 mass extinction events, the Cambrian explosion, the emergence of mammals, and the complete story of humanity, all occurring during only a small fraction of a single galactic orbit. When the non-avian dinosaurs disappeared 66 million years ago, the solar system had traveled only around 1/4 of one orbit around the Milky Way since the start of the Cretaceous period. The Andromeda Galaxy, located 2.5 million light-years away, is the most distant object visible to the unaided human eye. By the time the light reaching your eyes from Andromeda tonight first began its journey, the solar system had moved only a relatively short distance along its orbit around the galaxy. On the scale of cosmic time, even galaxies rotate with incredible slowness. But here is where galactic rotation becomes deeply strange. Strange in a way that points directly toward one of the greatest unresolved mysteries in modern physics. When a solid object spins, whether it is a wheel, a disk, or a plate, the entire structure behaves like a rigid body. The inner regions and the outer edges complete their rotation within the same amount of time. Physicists call this solid body rotation. Galaxies, however, are not rigid structures. They are enormous assemblies containing hundreds of billions of stars bound together by gravity, yet the stars themselves rarely collide, and each follows its own orbital path independently. If gravity from only the visible stars, gas, and dust were responsible for the galaxy's structure, then stars farther away from the dense central regions should orbit more slowly than those near the core. The situation should resemble the solar system, where the outer planets move around the sun more slowly because the gravitational influence weakens with distance from the concentrated mass near the center. The Swiss-American astronomer Fritz Zwicky first noticed something deeply inconsistent in the 1930s while studying galaxy clusters. The galaxies inside those clusters were moving far too rapidly to remain gravitationally bound if only the visible matter were present. But it was the work of the American astronomer Vera Rubin that transformed the issue into a crisis physics could no longer dismiss. During the 1960s and 1970s, Rubin carefully measured how quickly stars rotated at varying distances from galactic centers. According to Newtonian gravity applied to visible matter, she expected the inner regions to rotate rapidly while the outer regions slowed down steadily with distance. Instead, she discovered something that should not have happened at all. The rotation curves remained flat. Stars located near the outer edges of galaxies were orbiting at nearly the same speeds as stars much closer to the center. In certain galaxies, the outer stars were even rotating slightly faster. This represents a dramatic contradiction between observation and what visible matter alone should permit. If Newton's gravitational laws are applied only to the stars and gas astronomers can directly observe, then those distant outer stars are moving much too quickly to remain trapped within the galaxy's gravity. They should have escaped long ago into intergalactic space, yet they remain in stable orbit. Their motion requires vastly more gravitational mass than we can actually see. Something else must be contributing additional gravity. Something enormous, spread through a roughly spherical halo surrounding the galaxy, extending far into the outer regions where visible stars become sparse. That unknown component neither emits light nor absorbs it, and it does not appear to interact electromagnetically. in any detectable way. Its existence is inferred entirely through gravity because it alters galactic rotation far beyond what visible matter predicts. We call this invisible component dark matter. Dark matter is not yet a confirmed particle. The term is essentially a label for the gravitational discrepancy itself, a placeholder for whatever unseen structure is supplying the extra gravitational framework that keeps galaxies intact and produces the flat rotation curves that Vera Rubin observed. Over the years, scientists have suggested many possible candidates: weakly interacting massive particles, axions, sterile neutrinos, primordial black holes, yet none of them has ever been directly observed. Experiments designed to detect them, hidden deep beneath the ground to protect them from background radiation, have operated for decades without producing a confirmed discovery. There is also another possibility that deserves attention, one that standard cosmology approaches with skepticism but has never been able to completely rule out. Modified Newtonian dynamics, commonly called MOND, introduced by Mordechai Milgram in 1983. MOND argues that Newton's law of gravity no longer behaves normally at the extremely low accelerations found in the outer regions of galaxies, and that by altering the equations slightly, the flat galactic rotation curves can be explained without invoking dark matter at all. MOND performs surprisingly well when applied to individual galaxies. It performs far less successfully when applied to galaxy clusters, and no one has yet managed to expand it into a complete, relativistic framework capable of passing every test that general relativity survives. Because of that, it remains a minority viewpoint, an unusual but fascinating idea sitting near the boundaries of mainstream physics. What both explanations ultimately agree on is this: galactic rotation curves are pointing towards something about mass and gravity that humanity still does not fully understand. Rotation, the same phenomenon we have been following from the spin of electrons inside your hydrogen atoms to the sweeping spiral arms of the Milky Way, is acting like a diagnostic instrument. It is exposing the fact that the universe contains far more organization and structure than what is directly visible. The rotational motion is the fingerprint. The unseen mass is the thing that produced it. And if the arrangement of mass inside galaxies is governed by something invisible, something whose source and identity remain unresolved after decades of investigation, then the story of why everything rotates includes a chapter written in matter that has never been detected, arranged in a structure that remains only partially understood, maintaining the visible universe in rotational patterns that our best theories can explain only incompletely, which, depending on your personality, is either profoundly frustrating or profoundly thrilling. Personally, that is exactly the sort of mystery that should make you keep paying attention. Now picture a collapsing cloud of gas. Imagine a section of space stretching across several light years, filled mostly with hydrogen and helium along with traces of heavier elements. The gas is cold. It is spread out thinly, but it is not perfectly even, and it is not perfectly motionless. Tiny density fluctuations exist throughout it, along with slight differences in velocity between separate regions of the cloud. Then eventually some disturbance, maybe the shock wave from a nearby supernova, maybe a gravitational interaction with another cloud, or perhaps simply the gradual effect of its own gravity building over millions of years, begins forcing the cloud to contract inward. Gravity starts pulling material toward the densest region at the center. Now consider a basic question: what shape should emerge from this process? Your first instinct might be to answer with a sphere. Gravity is isotropic. It pulls inward equally from every direction toward the center. So it seems reasonable that a collapsing gas cloud should simply form a sphere. And in part that is true for the final star that eventually appears in the middle. But the actual collapse process unfolds very differently, because the cloud possesses angular momentum. Those tiny irregular motions we mentioned earlier, the turbulent movements spread across different regions of the cloud, create a net angular momentum. The cloud as a whole has a slight rotational motion, not a large one, but enough. And as the cloud shrinks, that angular momentum has to be conserved. The cloud cannot simply get rid of it. There is nowhere for it to go. So as the radius decreases during the collapse, the rotation speed rises to compensate. The increase is dramatic. If the original cloud stretched across several light years and rotated so slowly that the motion was almost impossible to notice, but later contracts into a disk only a few hundred astronomical units wide, the rotational speed increases by a factor proportional to the square of the ratio between the original radius and the new one. That produces an enormous amplification. Rotation that once seemed insignificant inside the diffuse cloud becomes the dominant organizing influence within the collapsing system, powerful enough to stop the collapse in directions perpendicular to the axis of rotation. This is the central insight. Rotation does not merely accompany gravitational collapse. It directly determines the final structure. Material falling inward along the rotation axis can continue all the way to the center, eventually creating the protostar. But material approaching from the sides cannot move directly inward all the way, because it carries angular momentum that prevents a straight plunge toward the center. Instead, that material spirals gradually inward, while conserving its angular momentum, eventually settling into a rotating disk surrounding the central object. The disk is not some random coincidence or accidental feature. It is the mathematically unavoidable outcome of angular momentum conservation acting within a collapsing gravitational system. This is why planets emerge inside disks rather than forming in chaotic three-dimensional arrangements around their stars. This is why Saturn's rings are flat. This is the reason accretion disks surrounding neutron stars and black holes take on flat shapes instead of remaining spherical. It is also the reason galaxies organize themselves into enormous disks rather than forming perfect globes. Gravity by itself does not favor disks. If gravity acted alone, matter would naturally collapse into a sphere. The flattened disk structure appears because angular momentum is conserved, breaking the spherical symmetry that gravity would otherwise create in the plane perpendicular to the axis of rotation. Every disk-shaped structure scattered throughout the cosmos is evidence of rotation that already existed before the disk itself came into being. But think carefully about what this implies for systems that do not rotate. In principle, a completely motionless cloud of gas with absolutely zero angular momentum could collapse inward and form a sphere without ever creating a disk. Mathematically, perfectly non-rotating systems are possible. Yet, in the actual universe, a universe filled with turbulence, gravitational interactions, and chaotic motion, achieving exactly zero angular momentum is extraordinarily improbable. The slightest drift, the tiniest disturbance, even a microscopic velocity difference across the cloud, will survive the collapse process and become magnified into measurable rotation. Physical systems in the universe almost never settle into a state of perfectly zero angular momentum, because eliminating angular momentum entirely would demand an incredibly precise cancellation of motions, something random dynamical processes almost never produce naturally. This is where the familiar picture of rotation begins to crack apart. Rotation is not an extra ingredient that must somehow be added into cosmic systems. Rotation is the natural state. The real mystery would actually be the absence of rotation. A star that never spins, a planet without rotation, a galaxy completely motionless, those would be the true anomalies. Rotation is simply what happens when gravity acts on a cloud of gas that possesses even the slightest amount of angular momentum. And this leads directly to the question that the opening part of this documentary has been quietly building toward, or more accurately, toward revealing that modern physics still cannot answer. If rotation is the natural outcome, if every gravitationally forming system inevitably spins because any initial angular momentum becomes amplified during collapse, then the central mystery is not the mechanics of rotation itself. Those mechanisms are understood, at least broadly. The deeper question concerns the source of the angular momentum that later becomes amplified. Where did the very first angular momentum in the universe originate? What introduced the rotational content that every spinning galaxy, every orbiting world, every precessing quantum particle continues to carry even now? The cosmic accounting book of rotation contains countless entries, every one of them representing something spinning, orbiting, or precessing. Yet nowhere in that ledger is there any record of the original deposit. And as we are about to see, the laws of physics that describe how angular momentum behaves remain completely silent about where it initially came from. Those laws only ensure that once angular momentum existed, it would be conserved with extraordinary precision forever afterward. But the laws governing spin reach far deeper than planets, stars, or galaxies. They extend down into a level of reality where rotation no longer behaves like ordinary motion, and instead becomes something tied to the very definition of matter itself. In 1922, two German physicists, Otto Stern and Walther Gerlach, carried out an experiment that should deeply unsettle anyone who compares what they expected to observe with what actually appeared. The experimental arrangement itself was surprisingly simple. Stern and Gerlach used silver atoms, individual atoms vaporized from a heated sample, and directed them through a region containing a strongly non-uniform magnetic field. The reasoning behind the experiment was completely classical and seemed perfectly reasonable. A silver atom possesses a magnetic moment, meaning it behaves like an incredibly tiny bar magnet. Inside a non-uniform magnetic field, a magnet experiences a force depending on how its magnetic axis is aligned relative to the field gradient. A magnet aligned directly with the field is pushed one direction. A magnet aligned the opposite way is pushed in the reverse direction. A magnet oriented sideways experiences a weaker deflection. And if you considered a large collection of atoms, classical physics suggested their magnetic moments should point in every possible direction, because there was no physical reason to favor one orientation over another. The result, therefore, should have been a continuous spread of impacts across the detector plate. Some atoms should have bent strongly upward, others strongly downward, with every possible intermediate deflection forming a smooth band between them. But Stern and Gerlach did not observe a smooth band. They found two distinct spots, not a smear, not a continuous distribution, only two sharply separated points appearing on the detector. Half the atoms deflected one direction, while the remaining half deflected the opposite direction. There was no gradual spread, no continuum of possibilities, only two discrete outcomes, as though the magnetic moment of the silver atom could exist in exactly two states and absolutely nothing in between. This became the first direct experimental demonstration that atomic angular momentum was quantized, confined to specific discrete values instead of changing smoothly across a continuous range. The idea itself was not completely unfamiliar in 1922. About 10 years earlier, Niels Bohr had already introduced quantized energy levels for the hydrogen atom, and physicists were beginning to suspect that quantum systems naturally favored separate, allowed states instead of continuous possibilities. But what made the Stern-Gerlach experiment so powerful was that it transformed the concept into something physically visible. Quantization could literally be observed. On the detector plate, there was an empty space between the two impact points where atoms would have appeared if intermediate orientations had been possible. That empty region served as evidence that those middle orientations simply were not real. What made the story somewhat awkward from a historical perspective was that the experiment succeeded for reasons the scientists themselves did not fully understand at the time. Stern and Gerlach believed they were observing the orbital angular momentum of the outer electron in the silver atom. Yet the mathematics for orbital angular momentum did not predict only two separate beams. Orbital angular momentum quantum numbers always generate an odd number of allowed orientations. 1, 3, 5, and so forth. Never precisely 2. The appearance of two beams suggested the existence of something associated with a quantum number of 1/2, something orbital angular momentum alone could never create. Another 3 years passed before Samuel Gaudsmit and George Uhlenbeck proposed the missing explanation. The electron itself possessed intrinsic angular momentum, known as spin, independent of any orbital movement, with a value of 1/2 when measured in units of the reduced Planck constant. A spin of 1/2 produces exactly two possible measurement results: spin up or spin down, with absolutely nothing between those states. The importance of this discovery connects directly to the larger thread we have been following. Rotation, the phenomenon shaping everything from protoplanetary disks to spiral galaxies, turns out to be quantized at the deepest level of reality. It does not exist in arbitrary quantities. It arrives in discrete units, controlled by exact algebraic laws, with no smooth transitions permitted in between. The universe does not allow half-integer spin particles to continuously rotate from one orientation into another. They shift abruptly, they snap between states, and before that transition occurs, the particle does not even possess a definite spin orientation. Instead, it exists in a superposition of both possibilities, and only measurement compels it to settle on one outcome. If ordinary intuition was already under strain from the realization that everything in existence rotates, it is now about to fail completely. Because the spin responsible for the Stern-Gerlach experiment is not the rotation of a tiny ball spinning through space. It is something far stranger. Part 6. The Impossible Electron. In 1925, two young Dutch physicists, Samuel Goudsmit and George Uhlenbeck, were graduate students studying under Paul Ehrenfest in Leiden when they introduced an idea that should have collapsed the instant they examined its implications carefully. Yet, instead of being wrong, it turned out to be correct. Their proposal was simple in principle. The electron possesses intrinsic angular momentum. It behaves as if it spins. This concept could explain the anomalous Zeeman effect, which had confused spectroscopists for decades. Atomic spectral lines split inside a magnetic field in ways that could not be explained by orbital angular momentum alone. If the electron carried its own spin and therefore its own magnetic moment, the unexplained extra splitting suddenly made sense. But almost immediately, they encountered a devastating problem. If the electron were modeled as a tiny classical charged sphere spinning around an axis, which is the most obvious physical interpretation of intrinsic angular momentum, the mathematics produced a contradiction. To create a magnetic moment equal to the measured value, using the estimated electron size known at that time, the surface of the sphere would have needed to rotate enormously faster than the speed of light. Not just slightly beyond the limit, not marginally close to it, faster by multiple orders of magnitude. Since special relativity forbids any massive object from even reaching the speed of light, let alone surpassing it hundreds of times over, the classical spinning sphere picture immediately destroyed itself mathematically. Goudsmit and Uhlenbeck were so troubled by this that they attempted to withdraw their paper after discovering the contradiction. They brought the calculation to Ehrenfest, explaining that they believed they had uncovered a fatal mistake. Ehrenfest, who had already submitted the paper for publication, reportedly answered with something close to, "You are both young enough that you can afford to have a stupid idea." In the end, the idea itself was not foolish. The mistake was not the existence of spin. The mistake was imagining the electron as a tiny rotating sphere. Modern physics describes the electron as a point particle, something with no measurable size at all, no surface, no radius, no extended structure in space. And a mathematical point cannot spin in any ordinary geometric sense whatsoever. A rotation axis cannot be assigned to something that has no physical size, and yet the electron possesses angular momentum, always exactly 1/2 unit. No matter how quickly the electron moves, what surroundings it exists in, or what experimental method is used to examine it, the measured spin remains identical. This spin is not produced by the electron's shape or by literal motion through space. It belongs to the electron's quantum condition itself, an intrinsic characteristic just as fundamental as mass or electric charge. The mathematical framework that transformed this from a strange experimental fact into something fully consistent came from Paul Dirac in 1928. Dirac was trying to construct a quantum equation for the electron that also obeyed the rules of special relativity. The Schrödinger equation functioned well for slow-moving particles, but it failed once relativistic effects became important. When Dirac developed his equation and enforced Lorentz invariance, The mathematics naturally generated a wave function with four components. Dirac did not insert those components by hand. They emerged inevitably because the union of quantum mechanics and special relativity required them. Two of those components represented the electron in spin-up and spin-down states. The remaining two described another particle with identical mass but opposite charge, the positron. 4 years later, that particle was experimentally discovered, earning Carl Anderson a Nobel Prize. Dirac predicted antimatter without searching for it directly. It appeared automatically as a mathematical consequence of taking relativistic spin seriously. At its core, the Dirac equation reveals that spin is not some optional extra attached to the electron. It cannot simply be removed or adjusted. Spin emerges inevitably once quantum mechanics and special relativity are combined into a single framework. Any point particle governed by a relativistic quantum theory must possess spin. The electron's spin 1/2 is mathematically unavoidable, in exactly the same way that its charge is unavoidable or the existence of antimatter is unavoidable. The structure of the theory produces it, whether we expect it or not. So this is where the story now stands. The rotation we followed through galaxies, solar systems, collapsing gas clouds, and accretion disks exists because angular momentum is conserved. Every gravitational system preserves the angular momentum inherited from the cloud that existed before it. But at the very bottom of that chain, at the level of the particles from which all matter is constructed, the rotation does not come from an earlier spinning object. It is intrinsic from the start. It is woven directly into the mathematical structure defining what a particle actually is. The electron is not spinning because something in the past caused it to spin. The electron possesses spin because a relativistic quantum universe described by the Dirac equation makes the absence of spin mathematically impossible. At the deepest scale we know, rotation is not merely something matter does. Rotation is embedded in the definition of matter itself. Part 7. Why matter exists at all. Now consider a thought experiment that sounds ridiculous at first, but is completely legitimate from a physics standpoint. Imagine removing spin from the universe entirely, not reducing angular momentum, not slowing down rotating objects. Imagine erasing the intrinsic quantum spin of all fundamental particles so that every particle has spin 0. What would happen? The answer is astonishing. Matter, as we understand it, would stop existing. Not symbolically, not metaphorically, literally. The physical behavior that allows matter to form atoms, chemical structures, solids, molecules, and stable objects all depends directly on quantum spin. Remove spin, and the foundation supporting the material universe disappears with it. The mechanism responsible for this is called the Pauli exclusion principle, one of the most important organizing rules in all of physics. It was introduced by Wolfgang Pauli in 1925, the same year that electron spin was proposed by Gaudsmit and Uhlenbeck, and that timing was not accidental. The Pauli exclusion principle states that no two identical fermions, meaning no two particles with half-integer spin, are allowed to occupy the exact same quantum state simultaneously. Same position, same energy, same spin orientation, forbidden. Two electrons may exist within the same atomic orbital only if their spins are opposite, because then they are no longer identical in every quantum property. The instant both electrons would need the same spin to occupy the same state, the Pauli exclusion principle blocks it completely. This single rule produces consequences that spread through all of chemistry and all of solid-state physics. Think about what this means inside atoms. The electrons surrounding a nucleus cannot all collapse into the lowest energy level together. The first energy level accepts two electrons with opposite spins, and then it becomes full. Any additional electron is forced into the second energy level. The third and fourth electrons occupy that level, and gradually the available positions within the second shell become filled as well. Eventually, those positions are exhausted too. Every new electron added to an atom is forced into a different energy state, positioned farther away from the nucleus and arranged in a new spatial configuration. That process creates the layered shell structure of atoms, And that shell structure is precisely what gives rise to the periodic table itself. Chemistry exists because electrons possess spin 1/2 and are governed by the Pauli exclusion principle. The repeating behavior of chemical elements, the valence electrons occupying outer shells, the way atoms connect and exchange electrons in order to complete those shells, all of it comes from the shell arrangement of atoms, which comes from the exclusion principle, which itself exists because electrons have half-integer spin. If spin did not exist, every electron would sink into the same lowest energy state. Every atom would share an identical electronic arrangement. Every element would behave chemically the same way. There would be no periodic table, no molecular structures, no chemical bonding, no carbon-based compounds, no water, no organic chemistry, no biochemistry, and no living systems of any kind. The exclusion principle is also the reason matter occupies physical space. Why does your hand stop at the surface of a table instead of sliding directly through it? It is not because atoms behave like tiny solid balls that physically block one another. Almost all of the volume inside an atom is empty space. The true reason is electron degeneracy pressure. When two atoms are forced close together and their electron clouds start to overlap, electrons belonging to separate atoms are pushed toward the same spatial region. But identical electrons cannot share the same quantum state, so they resist that compression. The Pauli exclusion principle creates an effective, repulsive interaction, not electromagnetic, not gravitational, but a purely quantum mechanical effect, produced by the half-integer spin statistics of electrons, preventing electron clouds from occupying the same configuration. That interaction is what gives matter its solidity. That interaction is why your hand remains resting on the table instead of passing through it entirely. In extreme cosmic environments, this principle becomes even more astonishing. When a massive star exhausts its nuclear fuel supply and begins collapsing under its own gravity, the entire stellar mass crushes inward toward the core. In a white dwarf, the remnant left behind by stars like the Sun, the collapse is stopped by electron degeneracy pressure. Electrons cannot all be forced into identical quantum states, and that resistance alone supports the star against further gravitational collapse, even after nuclear fusion has ended completely. In a neutron star, the compression becomes even more intense, and neutron degeneracy pressure, generated by the same principle acting on neutrons, which are also spin 1/2 particles, is what prevents total collapse and stabilizes the star. White dwarfs and neutron stars survive after stellar death because of quantum spin statistics. So the Pauli exclusion principle, emerging from the half-integer spin of fermions, is responsible for the architecture of the periodic table, the formation of chemical bonds, the solidity of matter, the surface beneath your feet, the stability of white dwarfs and neutron stars, and every structure in the universe capable of resisting gravitational collapse. That is not some minor side effect of spin. That is the entire physical framework of reality, constructed on the foundation of quantum angular momentum, which means rotation, not the ordinary rotation of planets or galaxies, but the intrinsic quantum spin carried by particles themselves, is not merely another property of the universe. It is the structural support holding the universe together. Without it, everything would collapse into a smooth and featureless plasma. With it, chemistry becomes possible, structure emerges, complexity develops, and eventually conscious observers appear, curious enough to ask why everything spins at all. Part 8. Spin as a bookkeeping rule of reality. Quantum field theory contains a theorem known as the spin statistics theorem, and it is unusual among the laws of physics for a very particular reason. It cannot truly be explained intuitively, not merely because it demands advanced mathematics to understand completely, intuitively. Richard Feynman, one of the greatest scientific communicators of the 20th century, openly admitted that he could not provide a simple elementary explanation for the spin statistics theorem. He attempted it repeatedly, more than once, yet he never discovered a way to make it seem naturally obvious or derivable from simple everyday reasoning. The only thing he could ultimately say was that the mathematics worked, the conclusion was correct, and the conclusion stated that particles with half-integer spin are required to obey Fermi-Dirac statistics and the Pauli exclusion principle, while particles with integer spin must obey Bose-Einstein statistics and experience no exclusion principle whatsoever. This separation, fermions versus bosons, half-integer versus integer spin, exclusion versus condensation, is not merely one possible classification among many. It is the only classification nature allows. Every particle that exists in the universe belongs to one of these two groups, and the group is determined entirely by the particle's spin. Quarks are fermions, electrons are fermions. Protons and neutrons belong to the category of composite fermions. Photons are bosons. Gluons are bosons as well. The Higgs boson is also classified as a boson. Gravitons, assuming they truly exist as quantized particles, would likewise fall into the boson category. There is no additional classification beyond these two possibilities. Nature does not allow a smooth transition or middle state between them. Spin determines statistics. Statistics determines the collective behavior of particles, and the collective behavior of particles shapes the complete architecture of matter and radiation throughout the universe. So why does spin dictate statistics in the first place? This is exactly where the spin statistics theorem enters the picture. The complete mathematical proof depends on Lorentz invariance, meaning the laws of physics must appear identical in every inertial reference frame, together with the principles of quantum field theory, which require quantum fields to either commute or anti-commute at space-like separations in order to preserve causality. When a field commutes with itself across space-like separations, the particles associated with that field are bosons. When it anti-commutes, the particles are fermions, and remarkably, fields that describe particles with half-integer spin are forced to anti-commute. There is no alternative if the theory is expected to remain both Lorentz invariant and causal. That anti-commutation relation is precisely what generates the Pauli exclusion principle. The mathematics leaves no room around it. Conceptually, this tells us that spin is not merely a feature particles randomly possess. Spin is a restriction imposed by space-time itself upon quantum fields. The demand that physics obey the symmetries of special relativity, especially symmetry under Lorentz transformations, compels quantum fields to adopt particular spin values, and those spin values then determine the statistical rules governing their behavior. In a deeply exact sense, spin represents the fingerprint of Lorentz symmetry at the scale of individual particles. It answers the question of what characteristics a quantum field must possess in order to transform consistently under the rotations and boosts required by special relativity. The answer is that the field must carry a definite spin, and that spin must always be either an integer or a half-integer, with the chosen spin controlling every aspect of how particles from that field interact with one another. Look at the gauge fields inside the Standard Model. The photon, responsible for the electromagnetic force, carries spin 1. Gluons, which transmit the strong nuclear force, also carry spin 1. The W and Z bosons, responsible for the weak interaction, each possess spin 1 as well. Every force-mediating particle in the Standard Model has spin 1. The graviton, the still hypothetical quantum carrier of gravity, would possess spin 2 if it truly exists as a quantized particle. The Higgs boson, the particle responsible for giving mass to other particles, carries spin 0. None of this structure appears by accident. The spin associated with a force-carrying particle determines the mathematical form of the force it transmits, the angular structure of the interaction, the number of independent polarization states available to it, and the specific way it connects to matter fields. Spin acts as the organizing framework underlying the entire Standard Model. And beneath all of this, beneath the exclusion principle, beneath the periodic table, beneath the solidity of matter, beneath the structure of forces and the classification of particles, there exists a conservation law. Spin, being a form of angular momentum, is conserved. During every interaction, every collision, every decay process, every emission event, the total angular momentum before and after always remains identical. The universe maintains flawless accounting of its angular momentum budget. Not a single unit of spin is ever created or destroyed. Every measurable spin carried by every particle in the cosmos today is spin that has existed in one form or another since the earliest moments of existence. Which leads us back to the central mystery. This entire documentary has been constructing piece by piece. If spin is conserved, and if every rotating thing in the universe inherited its spin from an earlier configuration, and if that inheritance chain extends all the way back to the first moments after the birth of the cosmos, then whatever angular momentum existed at the beginning has been preserved perfectly ever since, redistributed endlessly but never created and never erased, all the way to the present day. The angular momentum present in the spin of an electron inside your body right now is angular momentum that already existed within the quantum fields of the early universe, encoded directly into the initial conditions of reality itself. And here is the question modern physics still cannot answer. Why did those initial conditions contain exactly the angular momentum they did? Why was it not larger? Why was it not smaller? Why was it not exactly zero? What process, if any, established the opening balance in the universe's spin ledger? Because the laws of physics, at least as we currently understand them, can explain only how the ledger changes over time. They cannot explain why the ledger began with any specific value in the first place. The universe keeps its accounting with perfect precision, yet nobody has ever discovered the original deposit record. Conservation laws are, at the same time, the strongest and the most frustrating instruments in all of physics. They are powerful because they are absolute. They apply everywhere, during every interaction, across every scale imaginable, with no known exceptions. Yet, they are deeply unsatisfying, because a conservation law can describe how a quantity changes over time, but it cannot explain where that quantity originally came from. The conservation of angular momentum states that the amount of angular momentum existing in the universe today must be identical to the amount that existed before, and before that, continuing backward all the way to the very beginning. But the law itself cannot explain why the universe started with a specific amount of angular momentum in the first place. That leads directly to what could be described as the creation paradox of angular momentum. On one side, every rotating galaxy, every planet in orbit, every spinning star, and every quantum particle undergoing precession carries angular momentum that has been preserved since the earliest stages of cosmic history. On the other side, the inflationary era, the astonishing period of exponential expansion that took place during the universe's first tiny instant, should have diluted any original global rotation down to levels too small to ever detect. Inflation enlarged the universe by a nearly unimaginable amount, at the very least around 10 to the power of 78 inches volume, and perhaps enormously beyond even that. If a net universal spin existed before inflation, that expansion would have stretched it across such an enormous volume that its effective density inside the observable universe would now be essentially zero. So then where did the angular momentum of galaxies, stars, and planets actually come from? The leading explanation is tidal torque theory, first proposed by in 1951 and later expanded by and other researchers. According to this idea, galaxies did not inherit their spin from a giant, primordial cosmic rotation. Instead, they gained angular momentum through gravitational interactions, while cosmic structures were forming. In the young universe after inflation, matter was not distributed perfectly evenly. Tiny fluctuations in density existed, regions slightly denser and slightly emptier than average, created by quantum fluctuations during inflation, locked into place by the rapid expansion, and preserved as a subtle but genuine pattern in the matter distribution of the cosmos. As gravity slowly pulled those overdense regions together into the first seeds of galaxies and clusters, nearby structures began exerting tidal gravitational forces on one another. Those tidal forces created torques, twisting interactions capable of transferring angular momentum between forming proto-galaxies. The crucial point is that angular momentum was never produced from nothing during this process. It was redistributed, Two nearby protogalactic systems in the early universe could exchange angular momentum through tidal gravitational effects. One structure would begin rotating in one direction, while the neighboring structure acquired an equal rotation in the opposite direction. The total amount remained unchanged. The universe kept the same overall angular momentum balance it already possessed. Locally, however, individual galaxies developed spin not because the universe itself rotated globally, but because nearby concentrations of matter interacted gravitationally during structure formation. This remains the standard explanation for the origin of galactic angular momentum, tidal torques acting during the birth of large-scale cosmic structures. Even so, unresolved problems remain. The broad statistical predictions of tidal torque theory agree reasonably well with the general distribution of galaxy spins that astronomers observe, but the details still do not line up perfectly. The theory struggles to predict the exact spin strengths and orientations of individual galaxies with high precision. Astronomers also observe correlations between galaxy spins and the enormous cosmic web, the gigantic network of filaments and voids across which galaxies are distributed, and those alignments are not fully accounted for by the simplest versions of tidal torque theory. The origin of galactic rotation is understood in broad outline, but many of the finer details remain areas of active scientific investigation. What this larger picture ultimately reveals is something extraordinary about the rotational structure of the universe itself. Every spinning object you can observe traces its angular momentum back to quantum fluctuations generated during the inflationary epoch, later amplified by gravitational collapse, redistributed between forming structures through tidal torques, and conserved perfectly during every stage of the process. In a very real sense, the spin of a galaxy is the mature cosmic descendant of a tiny quantum disturbance that existed during the first fraction of a second after the beginning of time. The universe transforms microscopic quantum randomness into enormous cosmic architecture, and rotation becomes part of that architecture. Yet the deeper question still remains unanswered. Why did those original fluctuations contain the angular momentum they did? Why were the initial conditions of the universe arranged in that particular way? That mystery remains completely open. Here is the number that should genuinely make you pause. Take the angular momentum of every galaxy inside the observable universe, each one rotating in its own direction, at its own velocity, carrying its own mass. Then include all the orbital angular momentum from galaxies moving around shared centers of mass inside galaxy clusters. After that, add the spins of every star, every planet, every neutron star rotating at incredible speed, every black hole turning through space. Count every rotation on every scale. Perform the complete cosmic balance sheet. The result is, within the limits of observational accuracy, zero. Not merely tiny. Not close to zero in the casual sense, where huge quantities become negligible when spread over enormous distances. Zero in the sense that positive and negative angular momentum cancel each other out with astonishing exactness. Galaxies rotate in both directions in nearly equal proportions. The motions of galaxies inside clusters are distributed randomly, rather than favoring one universal orientation. On the larger scales, the universe reveals no preferred rotational axis, no special direction toward which more angular momentum points. Even the cosmic microwave background, the ancient radiation left over from the hot early universe and visible across the sky in every direction, contains no large asymmetry, suggesting that the cosmos as a whole is rotating. The large-scale statistical isotropy of the universe is not absolutely perfect at the quantum fluctuation level. The CMB really does contain temperature variations of around 1 part in 100,000, but none of those patterns resemble the signature expected from a global cosmic spin. The universe is overflowing with local rotation, yet globally it appears motionless. Every separate part turns. The whole does not. When you stop and think carefully about that, it becomes profoundly strange. There is nothing obvious about why reality should behave this way. One can easily imagine a universe whose initial conditions contained some overall angular momentum, a cosmos that was not only expanding but also slowly rotating as an entire structure. Nothing in known physics clearly forbids such a situation. General relativity actually allows rotating universe solutions. We will arrive at one of those solutions soon, and it is deeply unsettling. The fact that our universe appears non-rotating can be viewed as a statement about its original conditions. Somehow, the beginning of everything was arranged with extraordinary precision so that the total angular momentum of the universe came out essentially equal to zero. Why should that happen? No confirmed mechanism requires it. No known symmetry principle obviously demands that the universe must possess zero net angular momentum overall. Some cosmologists suggest that cosmic inflation may explain it, because inflation would smooth out large-scale rotation in the same way it smooths large-scale curvature and uneven matter distributions. Yet tidal torque theory naturally generates local angular momentum without producing any overall global spin. In that picture, the cancellation might simply emerge statistically from the way angular momentum gets distributed rather than from some profound underlying symmetry law. Different cosmic structures gained their spins through tidal interactions with neighboring structures, and those interactions automatically preserved the total balance, creating equal and opposite rotations across the larger system. Even so, the precision of the cancellation remains remarkable. The observable universe contains roughly 2 trillion galaxies, and somehow their combined angular momentum balances out within the finest limits of our measurements. There is something beautiful and slightly disturbing about that picture. A cosmos where every individual component is endlessly spinning, while the total system remains perfectly still, resembles a gyroscope spinning internally without precession, or a vast collection of spinning tops arranged so carefully that every directional vector cancels another when added together. The universe is accomplishing this not with a handful of objects, but with the angular momentum of galaxies spread across a region nearly 10 billion light-years wide, and apparently it is happening accidentally. Or perhaps it is not accidental at all. The possibility that the cancellation is not completely exact, that a tiny leftover global angular momentum might exist just beneath our present detection limits, remains a scientifically open question. And if that turns out to be true, the consequences are not merely astrophysical. They reach into questions about existence itself. Whether the universe possesses a small but non-zero overall rotation is not just an abstract theoretical issue. It challenges the deepest assumptions of modern cosmology and may provide a glimpse into the conditions present at the very beginning of everything. Modern cosmology is built upon an assumption known as the cosmological principle, that on the largest scales, the universe is homogeneous and isotropic. Homogeneous means that no matter where you observe it from, the universe appears essentially the same. Isotropic means it appears identical in every direction you look. Naturally, these are only approximations. At smaller scales, the universe obviously contains structure, with galaxies gathered into enormous filaments, clusters, and vast empty voids. But once you examine distances of several 100 million light-years or more, the cosmos begins to look astonishingly uniform. The cosmological principle is strongly supported by the isotropy of the cosmic microwave background, whose temperature fluctuations differ by less than 1 part in 100,000 across the entire sky. A rotating universe, however, would not behave this way. It would possess a preferred axis, meaning the laws of physics would appear slightly different along that direction compared with directions perpendicular to it. The remarkable uniformity of the CMB remains the strongest observational evidence against any meaningful global cosmic rotation. The Planck satellite, which created the most detailed maps ever made of the cosmic microwave background, placed extremely strict constraints on how much the universe could possibly rotate. The maximum allowed rotation rate is roughly 10 to the -9 radians per Hubble time. In other words, if the universe rotates at all, it would complete no more than 1/1000th of a radian during the entire lifetime of the cosmos. That is not merely slow. It is slow on a scale where ordinary language completely fails to describe it properly. During that immense span of time, the observable universe expanded, formed galaxies, galaxy clusters, and gigantic filamentary cosmic webs, created stars and planets, and eventually produced conscious observers capable of studying it. Yet throughout all of that history, if any global rotation exists whatsoever, the universe has still not completed even 1/10 billionth of a full turn. For nearly every practical purpose imaginable, this is indistinguishable from zero. Still, it has never been conclusively demonstrated to be exactly zero. There have been controversial claims, far from universally accepted, suggesting possible observational hints of cosmic anisotropy. Lior Shamir published multiple studies examining enormous collections of galaxy images, arguing that galaxies spinning in one direction seem to slightly outnumber those rotating the opposite way. According to these analyses, there may be about 3% more clockwise spirals than counterclockwise spirals, or the reverse, depending on the section of the sky examined and the specific dataset being analyzed. If such an asymmetry turned out to be genuine and systematic, it could imply that the universe possesses a preferred handedness in its large-scale structure, a faint global chirality, or perhaps an extremely weak overall rotation, subtly influencing the angular momentum of galaxies as they form. Most cosmologists remain unconvinced. The proposed asymmetries are tiny, the statistical methods behind them are heavily debated, and systematic bias offers a very plausible alternative explanation. Automated galaxy classification systems can introduce subtle asymmetric errors when assigning rotational directions to galaxy images, especially across massive datasets. Because of that, many researchers suspect the reported imbalance may result from observational or computational bias rather than a real cosmic effect. The issue remains unresolved today, and it will likely require future surveys that are larger, cleaner, and more rigorously controlled before any definitive conclusion can be reached. But the mere existence of this debate already reveals something profound about what is at stake. The assumption that the universe does not rotate is one of the central foundations of the standard cosmological model. If that assumption turned out to be even slightly incorrect, if astronomers eventually measured a genuine and reproducible non-zero cosmic rotation, the consequences would extend far beyond adjusting a few details in existing theories. It would demand a major rethinking of the cosmological principle itself and everything constructed upon it, and it would open a question that reaches beyond astrophysics entirely. Because as we are about to discover, a rotating universe is not simply another variation of the cosmos. A rotating universe may also be a universe in which the direction of time is not uniquely fixed. The arrow of time itself could point along multiple paths at once. And that creates a problem that even general relativity struggles to contain. Part Toll, Gödel's rotating universe nightmare. On the 28th of April 1949, Kurt Gödel presented a paper at a conference in Princeton celebrating the 70th birthday of Albert Einstein. Gödel was already world famous because of the incompleteness theorems he published in 1931, proving that any sufficiently powerful mathematical system inevitably contains true statements that cannot be demonstrated within the system itself. With only 2 theorems spanning a handful of pages, he shattered the dream of constructing a perfectly complete and fully consistent foundation for all mathematics. But at Einstein's birthday conference, Gödel arrived with something even more unsettling. He had discovered an exact solution to Einstein's field equations in general relativity, and the universe described by that solution appeared to permit something that should have been impossible. Gödel's model described a rotating universe. In this version of the cosmos, matter was spread evenly across space, much like in conventional cosmological theories, except there was one extraordinary difference. The entire distribution was rotating. Inside such a rotating universe, a determined traveler could follow a carefully chosen trajectory through space-time, accelerating, bending course, and eventually returning not only to the same place in space, but to the exact same instant in time from which the journey began. Not merely arriving home after many years, but returning to the identical moment of departure. This kind of trajectory is known as a closed time-like curve, a route through space-time that loops backward onto its own temporal origin. What Kurt Gödel uncovered was that a rotating universe naturally permits these closed time-like curves, meaning that within such a cosmos, traveling into one's own past is not simply an imaginative concept, but something that general relativity mathematically allows. The rotation of the universe generates an effect similar to gravitomagnetism within spacetime itself. It distorts the light cones, the geometric structures that determine which events are capable of influencing other events. Through this twisting changes their orientation in a way that permits certain paths through spacetime to circle back onto themselves. In a universe without overall rotation, the causal structure remains orderly and straightforward. Your past light cone contains every event capable of affecting you, while your future light cone contains every event you might influence in return. But in a rotating universe, those cones can tilt far enough that a path always moving forward in time may eventually curve back and reconnect with its own beginning. This creates consequences that are profoundly disturbing. Closed time-like curves open the door to causal paradoxes like the ones commonly explored in science fiction. A person could theoretically travel backward in time and prevent their own birth, or kill their grandfather before their parents ever existed. In more formal terms, these curves violate the chronological protection conjecture, Stephen Hawking's proposal that the laws of physics somehow prevent such situations from forming in any realistic physical universe. Hawking argued that this protection must exist because the alternative, a reality where causality could fail, seemed not only strange but fundamentally inconsistent. To be absolutely clear, our universe does not appear to resemble Gödel's rotating universe. Observations show no evidence of large-scale cosmic rotation. We do not detect closed time-like curves. Modern cosmology strongly supports the picture of a non-rotating, expanding universe described by the standard cosmological model. Gödel's solution remains a mathematical curiosity, proof that Einstein's equations permit rotating universes, not proof that our own cosmos is one of them. Stephen Hawking and Roger Penrose spent years studying whether realistic rotating universes could actually exist, and their work suggested that such universes would either collapse or develop severe pathologies preventing closed time-like curves from forming in practice. But this is exactly why Gödel's unsettling result matters so much here. The fact that a rotating universe would permit time travel, and that large-scale rotation becomes directly connected to causality through general relativity, completely changes how we think about the universe's near-perfect, zero-total angular momentum. Maybe that balance is not just an accident. If the universe had begun with significant overall rotation, then the causal structure of space-time itself might have been damaged from the very beginning. The arrow of time, the forward direction we experience in every process of nature, might not function in the clean and universal way we depend on. The ordinary sequence of cause before effect, the certainty of a fixed past and an open future, could become blurred and unstable. So perhaps the remarkable cancellation of global angular momentum is not merely an interesting detail of cosmology. Perhaps it is a requirement for a universe in which time behaves consistently enough for chemistry, biology, evolution, consciousness, and complexity itself to emerge. Perhaps we inhabit a non-rotating universe not because of random chance, but because a rotating universe would be too unstable, too causally fractured to support anything living inside it. Or perhaps the cancellation truly was accidental, the outcome of how angular momentum happened to distribute itself during cosmic structure formation, while the connection to causality is simply a mathematical danger we avoided through extraordinary luck. Either possibility leaves the same uncomfortable conclusion: that zero matters immensely, and as we are about to see, understanding where it came from and what maintains it forces us toward the deepest foundations of physical law ever discovered. Part 13. Rotation as a consequence of symmetry. There exists a theorem in mathematical physics that is both one of the most powerful achievements in science and one of the most philosophically unsettling. It was demonstrated in 1915 by the German mathematician Emmy Noether, and in its broadest form it declares that every continuous symmetry within the laws of physics corresponds to a conserved quantity. If the laws governing physics remain unchanged under shifts through time, if those rules function identically today, yesterday, and tomorrow, then energy must remain conserved. If the laws governing physics remain unchanged under shifts through space, if those same rules behave no differently here than they would 1 meter away or 1 light year across the cosmos, then momentum must remain conserved. And if the laws governing physics stay unchanged under rotations in space, if the outcome of an experiment does not depend on which direction you face it, then angular momentum must remain conserved as well. Noether's theorem is astonishing because it transforms conservation laws from seeming accidental into something unavoidable. The conservation of energy is not merely a fortunate observation scientists recorded after repeated measurements. It emerges mathematically from the fact that the laws of physics do not vary with time. The conservation of momentum follows mathematically from the fact that physics does not depend on location. And the conservation of angular momentum follows mathematically from the fact that nature itself does not favor one direction over another. The laws of physics appear identical no matter how your frame of reference is rotated. This rotational symmetry, known in mathematics as SO3, the group describing rotations within three-dimensional space, seems to be an exact feature of reality itself, not simply an approximation that survives within the limits of current experiments. An exact symmetry means that every experiment humanity has performed so far has found no genuine preferred direction hidden inside the laws of nature. And because this symmetry is both continuous and exact, Noether's theorem ensures that angular momentum is preserved fully and perfectly throughout every physical interaction. That is why the chain of rotational conservation we have followed throughout this entire documentary remains valid. From the quantum spin carried by the electrons inside your hydrogen atoms, to the turning protoplanetary disk that eventually formed Earth, to the solar system orbiting around the Milky Way, angular momentum has remained conserved through every encounter, every collision, every exchange of gravity, every electromagnetic interaction. No physical police force exists enforcing this law, and no hidden entity stands over the universe balancing accounts. The conservation exists because the universe obeys rotationally symmetric laws, and mathematically symmetric laws are compelled to preserve the quantity connected to that symmetry. But this is where Noether's theorem opens a deeper mystery instead of sealing it shut. The theorem explains why angular momentum remains conserved after it already exists. It says nothing about where that angular momentum originally came from. Conservation concerns dynamics, the way systems evolve and transform through time. Initial conditions belong to a separate category entirely. The laws of physics could possess flawless rotational symmetry and therefore conserve angular momentum with absolute precision, while still beginning with a universe containing zero angular momentum, or a universe containing 1,000,000,000,000 times more angular momentum than ours seems to possess, or even a universe carrying some specific non-zero angular momentum aligned toward a certain cosmic direction. The symmetry determines what happens after angular momentum exists. It does not explain the initial deposit itself. This problem is not unique to angular momentum. It appears throughout physics. Physical laws describe how systems evolve once initial conditions are given, yet the initial conditions themselves exist, in a profound sense, outside those laws. The standard model of particle physics does not derive the electron's mass directly from first principles. Instead, it accepts the measured value as a free parameter and inserts it into the equations. General relativity does not predict the universe's total mass-energy content either. It simply accepts whatever matter and energy exist and describes how space-time bends in response. The initial conditions of the cosmos, the exact values of all physical quantities at the earliest stage we can meaningfully discuss, enter the theory as inputs rather than outputs. They function as boundary conditions imposed upon the equations, not answers generated by those equations themselves. This is not necessarily a flaw or failure in our theories. It may instead reflect something fundamental about the nature of physical law itself. Scientific theories describe patterns in how systems change and evolve, while initial conditions are, by definition, prior to that evolution. Yet this leaves us with a profound, unanswered question. Why did the universe begin with the angular momentum it possesses? Whether that total is exactly zero, slightly non-zero, or something even more complicated. At present, our existing theoretical frameworks cannot provide that answer. Not simply because scientists have lacked enough intelligence, although deeper insight may eventually matter, but because solving this mystery may require an entirely different type of physical theory, one capable of explaining the origin of initial conditions themselves, rather than only describing how those conditions evolve afterward. There are a few possible explanations. In quantum cosmology, the Hartle-Hawking no-boundary proposal argues that the universe may never have possessed a true boundary in time at all, that it arose from a quantum geometric state without a singular starting point, and that its initial conditions were effectively chosen by the requirement that the cosmos remain internally consistent under quantum mechanics. If that interpretation turns out to be accurate, then the angular momentum contained within the universe could emerge naturally from the geometry involved in its quantum origin, meaning the expected total angular momentum would become a meaningful and calculable problem inside quantum cosmology itself. Whether those calculations would ultimately produce a value of zero, and whether the proposal itself correctly describes reality, both remain unresolved questions. But one thing is absolutely clear. Conservation laws alone cannot explain why everything spins in the first place. Noether's theorem explains why angular momentum is conserved once it exists. It says nothing about why any angular momentum existed to begin with. Throughout this documentary, we have followed rotation from the greatest structures in existence down to the smallest known scales. Galaxies turning across hundreds of millions of years. Solar systems emerging from rotating protoplanetary clouds. Atoms sending out the fingerprints of quantum spin through the radio spectrum. Electrons carrying intrinsic half-integer angular momentum because relativistic physics demands it. At every level we examined, rotation appeared. At every level, angular momentum conservation appeared as well. And at every level, the source of that angular momentum seemed to come from the scale beneath it, descending all the way to the quantum realm, where spin is built directly into the definition of particles through the structure of relativistic quantum field theory itself. But suppose we have been thinking about the relationship in the wrong direction this entire time. Suppose spin does not exist within space-time, with space-time merely acting as the stage where particles rotate and orbit. Suppose space-time itself emerges from something fundamentally rotational, something whose deepest structure resembles spin. Suppose the geometry of the universe is not primary, but instead an emergent phenomenon growing out of something more basic, more algebraic, and rotational at its foundation. Take a moment to really think about that, because it completely reverses the picture most people carry in their minds. Everything in this documentary so far has treated space as the container and rotation as the thing happening inside it. Galaxies rotate through space. Electrons spin inside atoms that exist within space. Angular momentum has been treated as a property carried by objects living inside the universe. But what if that entire picture fails at the deepest level? What if the container itself is constructed from the content? What if space is not the place where spin occurs, but instead the large-scale appearance that spin takes when viewed from far enough away? This is not science fiction, nor is it some fringe concept invented by someone lost in abstract philosophy. It is a legitimate and actively researched direction in quantum gravity, developed by some of the most mathematically rigorous physicists working today. The approach is known as loop quantum gravity, primarily developed by Carlo Rovelli and Lee Smolin beginning in the late 1980s. Loop quantum gravity attempts something physicists have struggled with for nearly 100 years. It seeks to quantize general relativity, to apply quantum mechanics directly to spacetime itself, to describe geometry, the same way quantum theory describes matter and energy, not as a perfectly smooth and infinitely divisible background, but as something made from discrete units at the smallest possible scales. The outcome is a picture where space is no longer continuous and smooth. At the deepest levels, space becomes a discrete structure. More specifically, it becomes what physicists call a spin network. A spin network is a mathematical graph made of nodes linked together by edges, and every edge carries a label. That label represents a value of quantum spin, not the spin of a specific particle, but spin treated as a pure mathematical property attached to the relationships connecting the nodes. And this is the part that should truly stop you for a second. Those spin labels are not cosmetic details. They are not just abstract accounting marks. They literally define the geometry of the space represented by the network. The area of a surface depends on the spins carried by the edges intersecting it. The volume of a region depends on the spins associated with the nodes contained inside it. In loop quantum gravity, both area and volume are quantized. They exist in discrete minimum amounts, just as energy exists in discrete photons and electric charge exists in discrete units tied to the electron. These minimum units of area and volume are determined by the Planck scale, around 10 to the negative 35 meters, a scale so unbelievably tiny that even if an atom were expanded until it matched the size of the observable universe, a Planck length would still remain smaller than an atom. Beneath the Planck scale, the very idea of smooth, continuous space completely collapses. There is no deeper spatial layer beneath this. Space is not an endlessly continuous substance that can be divided forever, the way people often imagine infinitely magnifying a geometric surface and always uncovering more surface underneath. At its most fundamental level, reality appears to consist of discrete quantum spin relationships, finite and granular in structure, while the smooth geometry we experience in ordinary life is only an emergent appearance. From the millimeter scales of daily experience to the megaparsec scales studied in cosmology, the continuity of space behaves like an approximation that emerges statistically. The apparent smoothness of the macroscopic world arises when unimaginably large numbers of quantized, spin-carrying connections and nodes are averaged together, much like the calm, continuous surface of water emerges from the collective motion of countless molecules that are themselves irregular and discontinuous. If this picture is correct, the consequences are astonishing and deeply disorienting. Spin is not merely a feature possessed by particles sitting inside spacetime. Spin is the fundamental ingredient out of which spacetime itself is assembled. The angular momentum values assigned to the links of spin networks are not simply tracking how matter behaves within an already existing geometric arena, they constitute that arena. When loop quantum gravity proposes that space itself is a spin network, it means that the three-dimensional structure you experience right now, the distances around you, the angles of the room, the volumes occupied by objects, all emerge from the large-scale averaging of an underlying architecture composed entirely of quantized angular momentum relationships. Space, at its deepest layer, is organized quantum rotation. That is what exists underneath the appearance of continuity. There is another framework, technically separate, yet conceptually related, that reaches a remarkably similar conclusion through a completely different route. This framework is known as twistor theory, developed by Roger Penrose beginning in the 1960s. Penrose approached the problem from a different motivation than Carlo Rovelli and Lee Smolin. His central goal was not primarily the quantization of gravity. Instead, he wanted to understand why quantum mechanics and space-time geometry seem to operate using profoundly different mathematical languages, and whether a deeper structure existed beneath both that could unify them naturally. What he eventually discovered was that the basic entities of physics, particles, and their interactions could be described not as points moving through space-time, but through objects he called twistors, geometric structures, encoding momentum, energy, and angular momentum together as a single mathematical entity. Inside twistor space, the fundamental ingredients are not events occurring at specific coordinates in space and time. The primary structures are null rays, essentially light rays together with their associated angular momentum information. In this picture, a point in spacetime is not itself fundamental. Instead, a spacetime point corresponds to an entire sphere of twistors. Events emerge secondarily from the intersections of these underlying structures. In the twistor description of reality, The universe is constructed from spinning, directional relationships, while the space-time we experience, the familiar four-dimensional stage of distances, intervals, and events, is reconstructed afterward as a larger-scale approximation. Rotation comes first. Space is the derived projection. Twister theory followed a long and complicated path through the history of physics. For many years, it existed as a mathematically elegant framework that struggled to reproduce the full spectrum of known physical interactions, especially those involving the strong nuclear force. Then, in 2003, Edward Witten demonstrated that amplitudes in string theory could be reformulated with extraordinary elegance inside twistor space, triggering a major revival of interest in the framework. Today, many modern amplitude calculations in particle physics, the equations used to predict the outcomes of collider experiments, are routinely performed using twister-inspired techniques that are vastly simpler than the older Feynman diagram methods traditionally used for those calculations. The mathematics of twistors, rooted fundamentally in angular momentum structures, has proven to be one of the most efficient languages physicists have discovered for describing particle interactions. What makes both loop quantum gravity and twistor theory so striking is that they converge on a provocative shared insight, despite beginning from entirely different assumptions and methods. The rotation and angular momentum observed throughout the physical universe are not decorative features added onto an already existing stage called space. In a profound sense, they come before that stage and give rise to it. The geometry of space does not exist first, and then permit quantum spin to occur inside it. Rather, quantum spin, expressed in its deepest algebraic structure, generates the geometry itself. The universe is not fundamentally a place in which objects rotate. At the deepest known level, rotation is the thing from which the universe is built. If even part of this picture turns out to be true, then it completely changes the meaning of the question we asked at the very start of this documentary. We began by wondering why everything in the universe rotates. We assumed the explanation would involve early cosmic conditions, conservation principles, or some ancient event that caused matter to begin spinning in the first place. But if spin exists at a level deeper than space itself, if the geometry of space is constructed from networks of spin, if space-time is only an emergent approximation rising out of a more fundamental rotational framework, then the original question transforms into something far more profound and unsettling. Things do not spin because objects were dropped into a ready-made universe and happen to rotate afterward. Things spin because spin, angular momentum, and rotational structure may be the most basic ingredients of reality itself. In that view, asking why everything spins becomes similar to asking why matter occupies volume at all. Spin is not occurring inside space. Spin may be the foundation from which space is built. Now, to speak honestly, and I believe you deserve that honesty after following this journey all the way here, these ideas remain speculative. Loop quantum gravity and twistor theory are both unfinished frameworks. Neither theory has yet produced experimentally verified predictions at the scales where their distinctive features could be observed directly. The Planck scale sits roughly 16 orders of magnitude below the smallest distances current particle accelerators are capable of probing. We are not going to test spin network geometry in a laboratory next year, or even next decade, and perhaps not during this century at all. At present, we cannot definitively confirm or eliminate these possibilities. Even so, these theories represent serious and mathematically rigorous attempts by physicists to answer one of the deepest questions imaginable. What are space, time, and matter at their most irreducible level? And at that frontier, the same answer continues to appear over and over again. Spin not merely as something contained within reality, but as the underlying architecture of reality itself, all the way down. There is a deeply humbling pattern hidden throughout astrophysics, and once you recognize it, it becomes impossible not to notice it everywhere. At every scale where angular momentum determines the structure of systems, whether in star birth, planet formation, galaxy evolution, or black hole accretion, our understanding remains incomplete in one very specific way. The missing piece is not a tiny correction or a few missing decimal points of accuracy. The problem is more fundamental than that. We still cannot derive from first principles something as basic as the exact rotation rate of a newly formed star once its formation process is complete. We fully understand the conservation law itself. We know the total angular momentum entering a process must equal the total angular momentum leaving it. But what we still struggle to describe in exact quantitative detail is the mechanism through which angular momentum is redistributed during that process. What carries it away? How rapidly it moves? What physical interaction transports it? And where exactly it ends up? At first glance, this may sound like a small technical limitation, the sort of thing scientists eventually refine with better simulations and improved observations. But it is not small at all. This gap appears at every scale explored throughout this documentary, from collapsing clouds that produce individual stars to the enormous architecture of galaxy clusters stretching across tens of millions of light years. The fact that the same limitation emerges repeatedly across such wildly different scales tells us something important. It suggests that angular momentum transport is not a finished area of physics with a few engineering details left unresolved. It is still an active frontier, one that remains open simultaneously across nearly every scale in the universe. Consider star formation, because it provides the clearest and most carefully studied example of this problem. A molecular cloud collapsing into a star begins with a measurable amount of angular momentum. Astronomers can observe the cloud, track the motion of gas throughout it, and calculate the total angular momentum present in the system before collapse begins. Then a star eventually forms, and when scientists measure the angular momentum of that newborn star, they encounter something astonishing. The final angular momentum of the star is many orders of magnitude smaller than the angular momentum the original cloud possessed, not slightly smaller, not reduced by half. Orders of magnitude smaller, meaning enormous factors of 10 separating the original rotating cloud from the star that emerged within it. This has been known for decades and is referred to as the angular momentum problem in star formation. If angular momentum were conserved locally during collapse, with no efficient process available to move that momentum elsewhere, a stable star would never form at all. As the material collapsed inward, its rotation would increase more and more dramatically during contraction, exactly like we discussed earlier in this documentary. It is the same figure skater effect, the same conservation principle, intensifying rotational speed as the radius becomes smaller. The matter would eventually rotate so rapidly that centrifugal forces would stop the collapse long before the object could ever reach stellar densities. Instead of forming a star, you would be left with a massive, fast-spinning disk without any star existing at its center. Angular momentum cannot simply disappear. It has to be transferred somewhere else. Some process must remove it from the forming star, otherwise the star can never come into existence at all. Astrophysicists have proposed several mechanisms to explain this, and the most truthful way to describe every one of them is that they are only partially understood. One possibility is magnetic braking. The collapsing cloud is penetrated by magnetic field lines, and while the cloud contracts, those magnetic lines are dragged inward together with the gas. But magnetic fields resist compression. They possess tension along their field lines, and that tension behaves like a giant lever arm, carrying angular momentum away from the inner collapsing region and outward into the surrounding material that rotates more slowly. The inner region loses angular momentum. The outer environment gains it. The accounting remains balanced, yet determining precisely how effective this process becomes inside an actual molecular cloud, with genuine turbulence, realistic density fluctuations, and constantly changing magnetic field strengths, requires calculations so difficult that they challenge even the most advanced supercomputer simulations available today. Another mechanism involves gravitational torques from binary companions. Most stars are not born alone. Observations indicate that the majority of stars similar to the Sun emerge within binary or multiple star systems, and the gravitational interaction between two forming stars inside the same cloud can exchange angular momentum between them over timescales that matter during star formation itself. A third mechanism comes from outflows and jets, and these phenomena are extraordinary to observe. Young stars, still surrounded by their accretion disks, eject powerful narrow jets of material perpendicular to the disk plane at velocities reaching hundreds of kilometers per second. Astronomers observe these jets throughout star-forming regions across the galaxy, shining in infrared and radio wavelengths, and stretching for light years beyond the young stellar systems that created them. Those jets are transporting angular momentum outward at enormous speeds, pushing it into the surrounding environment and functioning like an exhaust system for the rotational momentum that the star itself cannot absorb. Then there is disk accretion. In this process, matter does not plunge directly into the star. Instead, it slowly spirals inward through the disk, while angular momentum moves outward through the disk because of turbulent viscosity and magnetic instabilities. One especially important phenomenon is known as the magnetorotational instability, a process that creates turbulence inside the disk in a way that effectively drives angular momentum outward while allowing mass to drift inward toward the forming star. Every one of these mechanisms is physically real. Every one has been observed. All of them operate simultaneously inside actual star-forming systems, interacting with one another through highly complicated and nonlinear behavior. Yet none of them is understood with enough quantitative precision for a physicist to begin with. The initial conditions of a molecular cloud core and confidently predict the final spin rate of the star that eventually forms. The angular momentum of stars during formation remains a truly active field of research, with new data from facilities such as the Atacama Large Millimeter Array revealing structures inside protostellar disks that scientists are still attempting to interpret and model correctly. Exactly the same basic problem appears again when you expand your view to the scale of galaxies. Galaxies possess specific angular momentum, a certain amount of rotation per unit mass that correlates with both their total masses and their locations relative to the cosmic web, the enormous network of filaments and voids that organizes matter across the largest scales in the universe. Simulations of galaxy formation are capable of reproducing the broad statistical behavior of angular momentum in galaxies reasonably well. However, the finer details depend heavily on how the simulations treat feedback processes, meaning the energy and momentum injected into surrounding gas by supernova explosions, stellar winds, and the jets and radiation produced by active galactic nuclei. These feedback effects are not derived directly from first principles inside galaxy formation simulations. Instead, researchers rely on approximate prescriptions adjusted to reproduce observed behavior because calculating all of those processes from fundamental physics would require resolving scales ranging from individual stellar explosions all the way up to entire galaxies at the same time, something far beyond the capabilities of any computer that currently exists or is expected to exist anytime soon. Whether the spin of a specific galaxy can truly be predicted from the starting conditions of its surrounding dark matter halo, and whether current models fully reproduce the observed alignments between galaxy spins and cosmic web filaments, remain open questions that a large portion of the computational astrophysics community is actively investigating right now. Move down from galaxies and stars to the scale of individual worlds, and the mystery changes shape but never disappears. The Earth-Moon system possesses a very specific angular momentum balance, a combined total shared between the Earth's rotation and the Moon's orbital motion, and that balance places strict limits on every serious explanation for how the Moon came into existence. The leading explanation remains the giant impact hypothesis, where a body roughly the size of Mars, known as Theia, collided with the young Earth around 4.5 billion years ago in an angled impact, throwing vast quantities of molten debris into space that later gathered together to form the Moon. But this model is required to explain far more than the Moon's existence alone. It must account for why lunar material closely resembles the composition of Earth's mantle, why the Moon contains far less iron than Earth, and also why the Earth-Moon system today contains exactly the amount of total angular momentum we currently measure. Certain giant impact simulations generate those values naturally. Others only succeed when the collision angle, velocity, and masses of the impacting objects are adjusted with very narrow precision to reproduce the correct outcome. The range of possible scenarios is enormous, the observational constraints are demanding, and the exact nature of the collision that created the moon is still not completely resolved. And the moon itself is still continuing this exchange of angular momentum even now. Tidal forces operating between Earth and Moon steadily move angular momentum away from Earth's spin and into the Moon's orbit at a directly measurable rate. The Moon drifts farther from Earth by about 3.8 centimeters each year, a value determined with remarkable precision using laser pulses reflected off retroreflectors placed on the lunar surface during the Apollo missions. At the same time, Earth's rotation gradually slows by roughly 1.4 milliseconds per century. Billions of years in the past, the Moon orbited dramatically closer to Earth, possibly at only one-third of its present distance, while Earth itself rotated far more rapidly, with a full day perhaps lasting only 6 hours instead of 24. Under those earlier conditions, tidal dissipation would have been vastly stronger than it is today. Reconstructing the entire history of this angular momentum transfer, beginning with the giant impact and continuing to the modern era, has become a massive scientific effort involving multiple disciplines. Geologists investigate ancient tidal cycles preserved in sedimentary rock layers. Astronomers precisely track the moon's present recession rate, and dynamicists simulate the linked evolution of Earth's rotation and the moon's orbital motion across billions of years. In every possible sense, the investigation is still ongoing. Across all these scales, stellar, galactic, planetary, the pattern remains both consistent and astonishing. The conservation law survives every test. Angular momentum is preserved everywhere researchers have examined it. Every quantity must be accounted for. Whatever enters the system must eventually emerge somewhere else. Yet the exact physical processes responsible for transferring angular momentum from one region to another, magnetic braking, turbulent viscosity, tidal coupling, astrophysical jets, outflows, disk instabilities, remain only partially understood in strict quantitative detail. We know the accounting balances perfectly. What scientists are still working toward is a complete map of every pathway inside that accounting system and every exchange taking place between its different parts. And honestly, that may be the most remarkable aspect of all. This is not a breakdown of physics. It is not evidence that the underlying laws are failing. The conservation principle itself acts as an exact restriction, and inside those limits, the scientific challenge becomes understanding the mechanisms, the machinery, if you want to think of it that way, responsible for moving angular momentum through nature. That is simply science functioning at the edge of observation, mathematics, and computational power. What is extraordinary is not that unanswered questions remain. What is extraordinary is how far one single principle extends across reality. Angular momentum, as far as we currently know, is conserved. Spin survives. Rotation builds up instead of disappearing inside gravitationally bound systems. One law, applied consistently across 20 orders of magnitude in physical scale, from structures approaching the Planck length all the way out to the filaments of the cosmic web, reproduces the architecture of the visible universe itself. The same mathematical rule that keeps an ice skater spinning faster when she pulls her arms inward is the very same rule that keeps the Milky Way rotating at roughly 230 kilometers per second, billions of years after the original gas cloud that formed it has already been transformed into stars, dispersed into space, and recycled countless times. One law, 20 orders of magnitude. Every rotating structure we can observe, the accounting always balances. We simply do not yet fully understand every mechanism responsible for balancing it. Part 16, Final Synthesis. The Unresolved Universe. Now let us pause and examine carefully what humanity truly knows, what we believe we understand, and what still remains genuinely unresolved, openly uncertain, and unapologetically mysterious. Because after everything we have explored throughout this documentary, the spinning Earth carrying you eastward at more than 1,000 miles every hour, the quantum spin radiating from every hydrogen atom inside your body, the flat rotational curves of galaxies hinting at unseen mass, the Stern-Gerlach experiment dividing silver atoms into two seemingly impossible paths, the Pauli exclusion principle keeping the ground beneath you rigid and solid, Gödel's rotating universe folding time back into itself. After all of that, we owe ourselves a truthful reckoning. Not a perfect conclusion. Physics does not always provide one, but a clear and honest examination of what the evidence truly shows, point by point, before we finally close the book on it. Every particle that exists in the universe possesses spin. Every electron, every quark, every neutrino, every photon contains an intrinsic quantum angular momentum that belongs permanently to the particle itself. Not something gained through experience, not something temporarily taken from somewhere else and later returned. It is not the consequence of the particle beginning to rotate at some earlier stage in cosmic history. Spin is woven directly into the identity of the particle, embedded in its nature as fundamentally and permanently as its mass or electric charge. It is required by the mathematics of relativistic quantum field theory, not included as a decorative feature chosen by physicists, but arising inevitably from the union of quantum mechanics and special relativity. The Dirac equation cannot describe an electron without spin. The electron's half-integer spin emerges from the mathematics, whether anyone prefers it or not, and that spin remains conserved through every interaction the particle experiences, from the first excitation of those quantum fields during the earliest instance of the universe, all the way to the present day, and onward into whatever future still awaits the cosmos. Not a single unit of that spin has ever been created or erased during the entire history of existence. Every gravitationally bound system in the cosmos rotates. Every planet circles its star while spinning around its own axis. Every star rotates, rapidly in youth and more slowly with age, releasing angular momentum through stellar winds without ever truly stopping. Every binary system moves around a shared center of mass in a continuous gravitational dance that persists until gravitational waves eventually carry away the energy and angular momentum involved. And even after that merger occurs, the resulting object will still spin at extraordinary speed. Every galaxy rotates. Every galaxy cluster contains galaxies orbiting around a common center of mass. Every structure formed by gravity from material containing even the slightest angular momentum inherited that momentum, amplified it, and preserved it throughout its entire formation and evolution. The disc-shaped structures scattered across the observable universe, Saturn's rings, planetary systems orbiting distant stars, accretion disks surrounding neutron stars, the enormous spiral disks of galaxies, the brilliant accretion disks around supermassive black holes, powering quasars visible from halfway across the universe. All of them are physical records of angular momentum that could not collapse into the center, and instead arrange themselves into the flattest and most rotationally efficient geometry possible. Every disk is a fossilized trace. Every ring preserves a memory. Every spiral arm is angular momentum recording its own story in the language of starlight. The conservation law governing all of this stands among the most rigorously tested principles in all of physics. It states that angular momentum can never be created or destroyed by any physical process anywhere in the universe. As Emmy Noether demonstrated in 1915, this law follows directly from the rotational symmetry of nature itself. The laws of physics do not favor one direction over another, meaning an experiment produces identical results no matter how it is rotated through space. Every measurement humanity has ever made suggests that symmetry is exact. And because the symmetry appears exact, the conservation law is exact as well. Every experiment conducted in particle accelerators, atomic physics laboratories, and astronomical observations involving spinning pulsars or orbiting binary stars agrees with this conservation principle. Not roughly consistent, not merely close within experimental uncertainty, exactly consistent. Modern tests of angular momentum conservation in particle physics reach precisions of parts per billion, and sometimes even better. The law remains valid everywhere scientists have examined it, across every scale within every known interaction, without a single confirmed violation in the entire history of experimental science. And yet, here is the figure that ought to make you pause, put down whatever hot drink you prepared at the start of this video, and really think about what it means. The total angular momentum of the observable universe, according to the best measurements modern cosmology can produce, appears to be zero. Not tiny, not insignificant compared to the enormous sum of all the separate angular momenta scattered across the cosmos. Zero in the sense that positive and negative angular momenta balance each other with such astonishing precision that no observation has ever revealed any leftover remainder. Every rotating galaxy seems to have a statistical counterpart turning the opposite way. Every clockwise orbital pattern inside a galactic cluster is matched somewhere else by counterclockwise motion. The cosmic microwave background, the oldest visible light in existence, the fading thermal glow left behind by the young hot universe that surrounds us from every direction, reveals no preferred axis of rotation, no imbalance hinting that the universe as a whole is spinning. On the largest scales we can study, the universe appears isotropic, with a level of precision that excludes any meaningful overall rotation. Around 2 trillion galaxies, each one rotating, orbiting, wobbling, filled with the intrinsic spin of every particle inside them, and when every contribution is added together, the final total somehow cancels into nothing at all. We do not know the reason for this. We do not even know whether the cancellation is perfectly exact or simply extremely close to exact. The distinction between those two possibilities matters far more than most people realize. As we mentioned earlier while discussing Gödel's rotating universe solution, our current instruments still cannot determine the answer with certainty. Physics contains no established law demanding that the universe must begin with zero net angular momentum. There is no principle carved into the foundations of nature declaring that the cosmos had to start rotationally balanced. We possess no confirmed theory of quantum cosmology, no successful description of the universe's quantum birth capable of deriving this cancellation from deeper principles and presenting it as a necessary prediction. The zero is something we observe. It is not something we understand. The cosmic accounts balance with impossible elegance, yet nobody knows who created the accounting rules in the first place. Gödel's work showed us exactly why this mysterious zero matters so much. A universe with substantial net angular momentum would not merely resemble our own universe spinning faster. It would be a fundamentally different type of reality, one where the causal structure of space-time itself changes shape. Closed, time-like curves could naturally exist, trajectories through space-time capable of circling back onto themselves, allowing an observer to return to events that, in our universe, belong permanently to the past. The arrow of time, that irreversible flow from past toward future supporting thermodynamics, entropy, memory, causality, and the entire framework connecting one event to another, depends on space-time having a stable and consistent causal structure. Inside a rotating universe, that stability may disappear. Whether the near-zero angular momentum of our own cosmos is actually required for time to function as a coherent directed dimension, whether chemistry, complexity, biology, and consciousness themselves can only emerge inside a non-rotating universe, is a question sitting directly between physics, cosmology, and philosophy, and no accepted answer currently exists. Yet this is not some meaningless thought experiment. It is the kind of question that reveals itself naturally once you follow the chain of ideas far enough and realize it was hidden there from the beginning, waiting quietly at the end of the path. We already know from the spin statistics theorem and the Pauli exclusion principle that the half-integer spin possessed by fermions forms the foundation supporting all physical structure. It explains why matter occupies volume. It explains why atoms possess separate electronic shells. It explains why the periodic table takes the form it does instead of some entirely different arrangement. It explains why chemistry exists as more than a universe containing only one kind of element. It explains why the ground beneath your feet can support your body weight. It explains why white dwarfs and neutron stars avoid immediate gravitational collapse into black holes. Every physical structure in the observable cosmos, every chemical process, every living organism, every planet and star that manages to remain stable, all of it ultimately depends on the antisymmetry of fermionic wave functions. That antisymmetry depends on the half-integer spin of fermions, and that spin emerges from the framework of relativistic quantum field theory. Spin is not some strange detail sitting off at the edge of particle physics. It is one of the core load-bearing components of reality itself. Remove spin, and everything collapses through everything else into a smooth, featureless ocean without structure. Preserve it, and suddenly the universe becomes layered, organized, chemically rich, and eventually, against staggering odds, capable of becoming aware of itself. We understand from loop quantum gravity and twistor theory that several of the most mathematically sophisticated and serious attempts to solve the deepest mysteries in physics point toward a startling possibility. Spin may not be a characteristic of matter existing inside space at all. Instead, spin itself may be the underlying framework out of which space is formed. The three-dimensional world you experience around you, the room you sit in, the distance between objects, may simply be the large-scale average of an incredibly tiny, discrete network of quantized angular momentum interactions occurring at the Planck scale. In that picture, space-time is not the arena where spin takes place. Space-time becomes the large-scale appearance produced by spin itself. Reality would not contain spin inside it. Reality would emerge from spin if even part of this framework turns out to be correct, and at the moment no experiment can fully confirm or eliminate the possibility, then the question of why everything in the universe spins stops being a question about the behavior of objects inside reality. It becomes a question about the substance from which reality itself is assembled, and the answer appears to be spin. Asking why objects rotate would then resemble asking why matter occupies space at all. Rotation would not be occurring within space. Rotation would be one of the ingredients from which space is constructed. And throughout this entire 2-hour exploration, we have seen that the mystery of universal rotation exists on two completely separate levels that physics handles in very different ways. The first level concerns why spinning systems continue to spin, why angular momentum remains conserved with astonishing perfection, why systems held together by gravity naturally settle into rotational motion, why matter forms disks instead of collapsing into perfect spheres, why an ice skater accelerates her spin when she pulls her arms inward, why the Milky Way will continue rotating long after the sun is gone. These questions do have answers. The explanation comes from Noether's theorem, from rotational symmetry, from the conservation of angular momentum, from the physics governing collapsing clouds of gas, accretion disk behavior, and tidal torque theory. The broad mechanisms are known. The conservation law holds exactly. The equations function with extraordinary precision. The predictions align with what we observe in nature. This entire layer represents one of humanity's greatest intellectual triumphs. A single mathematical principle, rooted in the symmetry of space-time itself, successfully explains the rotation of everything from a toy spinning top to an enormous spiral galaxy. But the second level is entirely different. Why did the universe begin with angular momentum in the first place? Why did the initial conditions of existence include spin at all, instead of emerging from a perfectly rotationless state? Why is the total angular momentum of the cosmos so incredibly close to zero? Is it truly zero, or only nearly zero? And if it is only approximately zero, what keeps the remaining imbalance stable? What would happen if that tiny leftover amount were somehow released? These questions remain unanswered, not incompletely solved, not temporarily unresolved while physicists finish calculations. They are genuinely, fundamentally, literally beyond the reach of the physical theories we currently possess. They point directly toward the boundary of modern physics itself, toward the problem of initial conditions, toward the mystery of why the universe began in this specific way rather than another. And that question is extraordinarily difficult, because the laws of physics describe how systems evolve through time, not why the starting point existed as it did. Physics, in its current form, gives us an incredibly precise account of how rotational content changes and develops from whatever initial state the cosmos started with. What it cannot explain is what selected that initial state in the first place. Every equation, every conservation principle, every beautiful application of Noether's theorem, every successful prediction made by the Standard Model and general relativity begins by assuming that something already existed to evolve. Some original angular momentum, some initial distribution of spin, some starting rotational structure that the universe could preserve, redistribute, and transform over cosmic history. The laws explain the evolution with breathtaking accuracy. The source of what is evolving still sits outside the frame. Every particle possesses spin. Every large structure rotates. Yet the universe as a complete system appears not to rotate at all. Every component spins. The whole remains motionless. That statement may be the most elegant truth in cosmology, or perhaps the deepest unresolved fracture within it, possibly both at the same time. And in the distance between those two realities, between flawless conservation laws and the absence of an origin story, between the perfect mathematical bookkeeping and the unexplained initial condition behind it, sits one of the deepest unresolved mysteries in all of physics. Not merely a technical issue involving better measurements or more advanced computation, but a conceptual problem concerning what kind of explanation we are even justified in expecting when we ask why the universe exists in this form instead of another. Whether that mystery can truly be answered within the boundaries of physics, or whether it demands an entirely new way of understanding reality that humanity has not yet discovered, remains an unanswered problem itself. The cosmos has been rotating since before time even had language attached to it. Every galaxy scattered across the night sky is like a massive wheel that began turning long before Earth was ever formed. Every star acts like a gigantic gyroscope, conserving angular momentum inherited from ancient clouds of gas that existed before our solar system was born. Every atom inside your body continuously emits the signal of quantum spin at 1.42 gigahertz, quietly sending that signature outward into a universe that, in some strange sense, is built from the very thing being announced. And hidden somewhere inside that immense mechanism, within the spin networks that could form the underlying structure of space itself, within the original conditions that set every known rotation into motion from the quantum scale to the cosmic one, within that impossibly exact zero that preserves the causal order of time, there exists a question the universe has carried since its very beginning and still has not resolved. Not because humanity has lacked intelligence, although greater insight may eventually bring us closer. Not because our instruments are inadequate, even if future generations will undoubtedly construct far more powerful ones. Not because the mathematics cannot be approached, although the mathematics at this boundary of knowledge is extraordinarily difficult, but because the question stretches beyond the limits of what the laws of physics, at least in their current form, were designed to explain. The laws tell us what spin does. They do not tell us how spin first appeared. They track every exchange with flawless precision across the entire lifetime of the cosmos. Yet they never reveal where the original balance came from. And perhaps they are not even the correct tools for uncovering that answer. We understand how the universe rotates. We understand that the motion cannot simply disappear. We understand that when every contribution is added together, the final result somehow becomes zero. And every time a galaxy slowly turns, every time an electron sends its quantum signal into the darkness, every time Earth carries you eastward in silence at 1,000 miles per hour through a night that feels perfectly unmoving, that calm is not emptiness at all. It is the universe maintaining a flawless balance, endlessly spinning around a question it has carried since long before anyone existed to ask why.